Hello, ladies and gentlemen. We are going to do lesson unit 4, lesson number 2. We're going to talk about least squares regression line and using the calculator. And you are really going to have to listen carefully, and if you have to rewind this video and watch it again, please do so. All right, so we're going to start off with the following. We have a table here of the prices for a single pizza based on the number of toppings. We will imagine this is a high-class restaurant with a gourmet pizza. All right, so we can see a one-topping pizza is $9.50, 2 toppings is $11, 3 toppings is $12.50, and so on. So the first thing we're going to do is we're going to plot this data. And this is the only graph that we're going to do today where we're going to actually put the numbers on the graph. Otherwise, we're just going to sketch them. All right, so we need a label. The bottom is going to be number of toppings. And what we're going to do is we're going to put 0 right there in the corner. And then I'm going to skip every other line just so I can use as much of the graph as possible. Okay, I know it doesn't go up to 9, but I just went that far because I could. All right, and then on the side we have the price. Now on this one I am going to start with $9 on that first line, and then I'm going to skip a line. That'll be $9.50. Okay, so I'm going to skip a line and put 10, skip a line 11. So every other line will be 50 cents. Again, at any time, if I'm going too fast, just pause the video to catch up. All right, now we're going to plot the dots. So the first one is at one topping, $9.50. All right, one topping, $9.50. So one topping, $9.50. So right there is going to be my dot. Okay, the next one is 2 toppings, $11. 3 toppings, $12.50. Now I kind of see a pattern there, so I'm just going to keep following the pattern. So $4 will be right there at 14. Okay, that one's right there at 5 at 15.50, and 6 is at 17. Now I notice that these dots are in a perfectly straight line. Okay, but before we get into that, let's go to B. All right, it says, describe the relationship between the number of toppings and the price. So we say, as the number of toppings increases, the price increases. All right, that's describing the relationship. As the number of toppings increases, the price increases. All right, the next thing is find the equation for the least squares regression line, LSRL for short. Draw the line on your graph, write the equation below. All right, well first, let's get this to show up on our calculator. So let's go to the calculator, go to Stat Edit. All right, we're going to use list 1 and 2 like we did the other day. All right, if there's some numbers in it, remember go to the top, hit clear, hit the down arrow, and it'll clear out the numbers. All right, so let's type the numbers in. All right. Now, just to look at the picture on the scatter plot, so let's make sure our scatter plot's turned on. So hit your second, y equals, okay, number 1. Now mine is not ready to go, so it is on. However, it's not the scatter plot. So I need to go down and I need to hit enter on the scatter plot. So it's on and it's got L1 and L2. Okay, so now remember zoom 9 and it should show up. Hey, there it is. Those are the dots we just got done with. All right, so what we want is the least squares regression line. All right. So to do that, we're going to go stat, calculate, and we're going to pick number 4. Make sure, now those of you with the new calculator, it says L1, L2. Those of you with the old calculators, all you have to do is hit enter, and it should show up. It should say that. All right, so let me write that down. So we went stat, calculate, and again, that was number 4. All right. So the numbers for our equation are A is 1.5. Now remember this is money, so that's $1.50. B is 8. Okay, and our correlation, which we talked about last time, is 1. It's perfectly straight, so it should be a 1. All right, now this is money. So remember that 1.5 is $1.50 and that 8 is $8. All right, so define X and Y first. So remember X is going to be number of toppings. Y is the price. All right, so here we go. So we're going to say Y. Now we're going to put a little hat on that. The reason we put a hat on that is because these lines are made for predicting. Even though this is a perfectly linear line, we don't necessarily need that hat on there, but we're going to do that with the other examples. Again, Y hat is for predicting. All right, and it says, looking at our calculator again, it's going to be $1.50x plus 8. All right, well, I'm not going to put the dollar sign in front of it, but I am going to put the 0 behind it. So $1.50x plus 8. All right. So again, the correlation, we just saw that. The correlation is 1. Why is it that? The data points are in a perfect positive linear line. All right, I'm going to type that into my calculator. So I'm going to go here and I'm going to go to my Y equals and I'm going to put in $1.50x plus 8. And I'm going to hit graph and the line should go through those dots, and it does. And I'm going to draw that on my graph. All right. Interpret the rate of change. Okay, well, the rate of change is the number in front of X. So the rate of change equals $1.50. Okay, but that's not interpreting it. What does it mean? It means each topping will cost $1.50 more. Okay, pretty straightforward. At least I hope it is. Interpret the Y-intercept. Okay, well, the Y-intercept is 8. All right, let me switch colors here. Let's go. The Y-intercept is 8. Okay, well, what does that mean? A pizza with 0 extra toppings will cost $8. Okay. So the x is 0. Think about it. X represents the number of toppings. The y-intercept, the x value is always 0. So another way of saying it, that this is just a plain old cheese pizza, if you think about it. All right. Now, using the least squares regression line, let's find the cost of pizza with 8 and 10 toppings. So again, I'm going to be using my y hat is $1.50 times 8 plus 8. All right, type that into the calculator. I'll just do this one time. So I've got $1.50 times 8 plus 8. So a pizza with 8 toppings is going to cost you 20 bucks. All right, and 10 toppings. Okay, type that in. You're going to get 23 bucks. All right, hopefully that was pretty straightforward. Now, let's apply it to a different problem where the dots are not going to be perfectly straight. All right, so the following data shows the temperature lows and cereal sales for 13 randomly selected days. So hot cereal sales, that would be like oatmeal, okay, different things like that. All right, so temperature outside and boxes of hot cereal sold. All right, well, first of all, the temperature outside goes on the bottom. That is the explanatory variable. Boxes of hot cereal sold is the response. That goes on the y-axis. Now, we're not going to put any numbers on here. We're just going to be doing a sketch of this, so no numbers required. So the first thing we're going to need to do is type these numbers into the calculator. All right, I've got to type them in myself, so here we go. Stat edit. Again, go to the top, clear. Go to the top, clear. All right. Okay, I'm going to use my keyboard to type these in quick. You certainly can fast forward through this part if you want. Pause it, type them in, and then fast forward through it. Hopefully I do not mess up. All right, so I've got them typed in. My scatter plot is already set up. Okay, I do not need to do that again. To see it, I'm going to go ahead and do the zoom 9. All right, I've got the line going through my graph. That's from the last one, so I'm going to go ahead and clear that out of the y equals and look at the graph again. There, that looks better. All right, so the first thing is we're going to draw the scatter plot on our paper. So I'm going to do the best job that I can. You do the same thing. Try to put the dots, you know, kind of in the pattern using the whole graph. So I'm looking at the calculator and I'm trying to mimic what I'm seeing. Hopefully it's not too far off. Oops, let me back that up. I don't know what that just did. There we go. Okay, something like that, as long as it's pretty close. All right. So we did part A. Now let's look at B. B says, describe the relationship between the temperature outside and the boxes of hot cereal sold. All right, so as the temperature goes up, the boxes of hot cereal sold goes down. Okay, it's a negative correlation. As the temp goes up, the hot cereal sales go down. Think about it. People don't probably want to eat hot cereal when it's warm outside. All right, C, find the least squares regression line, draw the line on your graph, and write the equation below. Define X and Y. Well, first of all, let's define X and Y. X is the temp outside. Y is the boxes of hot cereal sold. So, Y hat, here we go. So, calculator. Stat, calculate, number 4. Voila. All right, so we're going to do a little rounding on this. So here we go. Let's write down the least squares regression line, the line of best fit. So I'm going to round that to a negative 1.9x plus 102.2. Okay, what is the correlation? That is negative 0.967. Is it strong or weak? Strong. Why? It is close to negative 1. All right. Interpret the rate of change. Well, first of all, the rate of change is the negative 1.9. So how do we interpret that? So now remember what X is. X is the temperature outside, all right? So we're going to say that for every 1 degree rise in temperature, again, X is representing the temperature. So for every 1 degree rise in temperature, the number of boxes of hot cereal sold decreases, because it's negative, decreases by approximately 2 boxes. Okay, we can't sell part of a box and we're going to round it. So for every 1 degree rise in temperature, the number of boxes of hot cereal sold decreases by approximately 2 boxes. All right, interpret the Y-intercept. Oh, not done with the other one. So going back, is this realistic? Yes, it is realistic. Okay, think about it. It's warmer outside, 2 fewer boxes of hot cereal are sold. That is realistic. Okay, nothing wrong with that. All right, the Y-intercept. So remember the Y-intercept in this problem is the 102.2. Okay, so what does it mean? When the temperature outside is 0 degrees. Okay, again, the x value is 0. What does that mean? Because x is representing the temperature. If x is 0, that means 0 degrees. When the temperature outside is 0 degrees, the number of boxes of hot cereal sold will be approximately 102. Okay, again, we can't sell part of a box, so we're just going to round it to 102. Is this realistic? Yes, that's realistic. Certainly is. If it's cold 0 degrees outside, I could see lots of hot cereal boxes being sold. All right, let's keep going. Use the least squares regression line to estimate the number of boxes of hot cereal sold when the temperature outside is 8 degrees. So again, I've got y hat equals negative 1.9x plus 102.2. All right, so here we go. So we're going to do 8 degrees. So y hat equals negative 1.9 times 8. Again, the y hat is for predicting. All right, plus 102.2. All right, so what do we predict? We predict that they're going to sell 87 boxes. Okay. Now let's do the negative 5 degrees. So again, y hat equals negative 1.9 times negative 5 plus 102.2. How many boxes of cereal do we predict? Well, first we get 111.7, but then we're going to round it, so approximately 112 boxes. All right, let's do one more with this one. So y hat, so we want, what if it's 80 degrees outside? All right, y hat equals negative 1.9 times 80 plus 102.2. All right, let's see what we get. We get a negative 49.8. Whoa, is that realistic? No. Why not? You can't sell negative boxes. So we would have to say they sell 0. Okay? The prediction is not good. Okay? It is not realistic. This is called extrapolation. Okay? This is a term you need to know. The use of a regression line for predicting outside the range of values of the explanatory variable used to obtain the line. Such predictions are often not accurate. Obviously, we cannot sell negative boxes of cereal. All right. All right, one more example, and then you should be able to do the rest of this packet. And if you have to rewind and rewatch things, please do so. The following data is a random sample of homes sold last week in Columbia Heights. All right, well, first of all, the explanatory variable is the square footage. And the response variable is the price of the home. All right, so let's take a minute and let's type these in. So go to your calculator, clear out list 1, clear out list 2, All right, I'm going to use the keyboard to type these in quick. Now, no commas, just type in the numbers. Do not put a decimal. Those are not decimals. Okay, those are commas, but you don't type commas in on the calculator. All right, hopefully I didn't mess up. Everybody's got a partner, looks good. All right, again, our stat plot is already set. Nothing to do there, just hit zoom 9. All right, so let's go ahead and sketch these dots on our paper. Again, just do the best you can. Let's see, right about here. Let me back that up. There we go. This thing does not like me plotting dots very well. Okay, looks good enough. All right, describe the relationship. Here we go. So we say as the square footage of the home or homes increases, the price of the homes increase. Okay, positive. As one goes up, the other goes up. Letter C, find the least squares regression line. Draw the line on your graph and write the equation below. Define x and y. All right, so first of all, x equals square footage. Y is the price. So on your calculator, remember you got to go stat, calculate, number 4. All right, so A is 94.51 and B is negative 2,697.16. So our y hat equals 94. Let's double check that. 94.51 x plus negative 2697.16. All right, now let's put that in our calculator and draw the line through the dots. So here we go, 94.51x plus negative 2697.16. All right, graph. Beautiful. All right, let's put that through our graph. All right, close enough. Okay, what is the correlation? So looking at the calculator, we see the correlation. Let's go back. Stat, calculate, number 4. 0.965. All right, so 0.965. Strong or weak? Strong. Why? Close to positive 1. All right, let's wrap this up. Next page, interpret the y-intercept. Or I'm sorry, the slope, the rate of change. So the rate in this problem, again, is the 94. Whoops, let's write that decent. 94.51. And remember, here, whoops, here x is going to be 1. So what does that mean? For each additional square foot in a house, the price will increase $94, whoops, $94.51. Is this realistic? Yes, it certainly is. Okay, each square foot, based on this data, each square foot could cost $94.51. That is a realistic thing. So think about that. Interpret the y-intercept. Well, the y-intercept is the negative 2,697.16. Okay, well, that's where x would be 0. So what does that mean? A house with 0 square footage, that means a non-existent house, will cost a negative $2,697.16. That's what it means. A house with 0 square footage will cost negative $2,697.16. Well, is that realistic? No, that is not realistic. Okay. You can't, so basically they are going to give you $2,697.16 for a house that doesn't exist. Okay, it's not realistic. It's not going to happen. But you do need that to use your prediction. You have to have that in your equation. So 94.51. So let's predict a house that's 3,500 square feet. How much is that house going to cost? All right, so let's type that in. So we've got 94.51 times 3,500 square feet plus negative 2,697.16. All right, so it's going to cost $328,087.84. $328,087.84. And yes, that is realistic. A big house is going to cost a lot of money. All right, well, good luck on the rest of this, ladies and gentlemen. Rewind and watch what you need to, but you have enough information to be able to do the rest of this packet.